Morning, folks. Doing okay? Had a good weekend? Any big news from the weekend? No? All right. Well, I have a few things for you. I brought your quizzes from last week. I'll hand those out at the end of class. If you go on the website, go to old quizzes, you can find the PDF of that, which also has the solutions, and then there's a video solution on YouTube for it as well. All right. So if you want to come talk to me too, though, we can also go over it. Like if you want to see what mistakes you made and you didn't do as well as you'd like, then please come see me. We'll go over it, and I can help you do better in the course. So I'm always available for y'all if you ever need help in the course. Y'all realize that, right? Am I clear on that? That it's my job to help you succeed in this course. So if you feel like you're not doing as well as you think you can, then please come see me. Or even if you just completely lost. Did I tell you about my dream the other night that I had? See if y'all can identify with this. I was in this class. I think it was an English class. It was some sort of humanities class, and I hadn't really been going to class that much, and I hadn't really been keeping up with the reading assignments. But that day I showed up to class, and we had a test. I pulled up the test, and I had no idea what it was talking about. And it was like the most frustrating thing to sit there and look at that test and read the questions and just have no earthly idea what any of the questions were talking about. Have you ever felt that way? Yeah? Okay. I know it's very frustrating. So if you feel that way in this course, then the best course is to come see me, and we'll sort it out. All right? So the old quizzes are on the web. I'll hand them back. I also have quiz 1 and some proposals here that weren't picked up. So if you didn't get those things, then please see me. Just want to remind you of some dates that are coming up. Quiz 3 is in 2 weeks. That's 2 weeks from today. That'll cover likely chapter 5 and 6, temperature and heat, which we're on now, and then fluids and pressure. Your proposal, or excuse me, your progress report, which would just be a description of the progress that you've made so far on your project, is due the Thursday after that next quiz, March 28th. And we are scheduled to not be in this room on March 26th and March 28th. But in fact, I'm just going to cancel class completely on March 26th. So we won't have class at all on March 26th. All right? I'm a CASA, and I have a court date on that day. We'll likely have some sort of online assignment. So I'll let y'all know ahead of time, like probably just like a short assignment or a reading assignment or whatever. Any questions about that? No? All right. Let's see, last time we left off with the different scales of temperature. We talked about 3 different scales of temperature. Can somebody tell me what one of those was? The one that we most commonly use here is called what? The Fahrenheit scale. The Fahrenheit scale is based on 2 points. What are those 2 points? Right, the freezing and the boiling point of water. And in the Fahrenheit scale, we call the freezing point of water 32 degrees. It's really just being assigned it to be 32 degrees. Is this thing really loud, Theo? I got about 6 microphones here. All right, so the Fahrenheit scale is based on the boiling and freezing points of water, and we just assign the freezing point to be 32 degrees Fahrenheit, and we assign the boiling point, gosh, I always forget, what is it, 212 or something? Is that right? 212, yeah. And then what's the other scale, another scale that we use? The Celsius scale, and it's based on what? The boiling and freezing points of water as well, except we assign different numbers for them, and that's really the only difference. We just assign different numbers for the boiling and freezing points. Freezing is 0, boiling is 100. So that scale is a little easier to use because there are 100 degrees between the boiling and freezing points of water, whereas with the Fahrenheit scale, there's, I don't know, 180 or whatever between those 2 points. And then there was a third scale that we use. This is the SI scale, but we don't really, like in real life, we don't use it that often. What was that called? The Kelvin scale, right. And the Kelvin scale is based on a completely different system. It was based on 2 temperatures, the absolute zero, which is the absolute lowest temperature that you can go. It's when all the motions, the random motions of the atoms, they stop, right? And so everything is frozen completely. So absolute zero is the absolute lowest temperature that you can go. And then a second temperature, which was called the triple point of water, right? And the triple point of water is a particular temperature and pressure when water can exist in all three phases. It's kind of cool, actually, isn't it? The temperature is just slightly above the freezing point of water. And in that, and then there's a particular pressure as well, where you get water as a liquid, gas, and a solid. All right? All right. I gave y'all some formulae on how to convert between those different temperature scales, and you'll need to use that for the quiz, but of course you'll have those equations. So it's really just a matter of making sure that you can use them to convert between Celsius and Fahrenheit and between Celsius and Kelvin. All right? All right, we also went into thermal expansion. I want to work through an expansion, through an example for thermal expansion right now. Thermal expansion is relevant in a lot of different ways. We listened to the car talk clip. Remember what happened with the guy in his car? What happened when he hit a water puddle? Remember something was wrong with his exhaust, and he had like this backyard guy weld on a different pipe, and then when he hit a water puddle, what happened? It what? Yeah, it would make noise. And the reason was that he had two different metals that were changing temperature, and one of them was expanding or shrinking at a different rate than the other metal. And so when he hit that water puddle and it cooled off, one of them would expand really quickly, and one of them would stay bigger. And so then things would start rattling or exhaust would start leaking out or whatever, because you had those two dissimilar metals, and different metals expand at different rates when they're heated up. Right? Actually, all objects expand at different rates when they're heated up. So a good application of that is in a thermometer, a mercury thermometer. We'll look at some different thermometers in just a bit. But a mercury thermometer or an alcohol thermometer, which is the one that we use primarily, when the temperature of the material inside that glass tube, when it increases, it expands. And we calibrate that so that we can measure temperatures. So let's just, what is the change? In the length of a column of mercury, like in a mercury thermometer. If the mercury is 3 centimeters long, so I have this 3 centimeter high column of mercury. If its temperature increases from 37 to 40 degrees Celsius. From 37 to 40 degrees Celsius. I gave you this expression last time for the change in length. The change in length is equal to L times alpha times delta T. This is my change in length right here. And in particular, this is what this question is asking, is what is the change in length? How much higher does this, or how much longer does this column become? This is my original length. You should already have this in your notes, but just rewriting it. This is my change in temperature. And this is called the coefficient of linear expansion. The coefficient of linear expansion. And this is determined experimentally for a certain material. So you would take a piece of metal, say a piece of steel or whatever, you would measure its length, then you would heat it up and then measure its new length, and then from that you would calculate what this alpha is, this coefficient of linear expansion. It's the Greek letter alpha. Okay, so here I would provide you with a table, and you would find that the coefficient of linear expansion for mercury is 60 times 10 to the minus 6. and that's measured in 1 over degrees Celsius. And then we could find delta L. So delta L would just be, I'll give you all a minute to do it. Go ahead and calculate what is delta L. What is my change in length for this column of mercury? I have a number for me? One day I'm going to fall off this stage because I always like to walk on this little thing. Y'all are going to think it's kind of funny, aren't you? Are you? It's okay. You can, yeah. You have a number for it? I'm going to go start writing it down. L is going to be 3 centimeters. Alpha is 60 times 10 to the minus 6. And then what's my delta T? What is it? 3, right, 3 degrees Celsius. And somebody have that? I don't have it right off. What's the number? Was it 5.4? 10 to the negative 4? Okay. What are the units for that? Do you have any idea? CJ? It's in centimeters. If I look here at my units, my degrees Celsius cancel out, and I'm just left with centimeters. So my units are here in centimeters. 5.4 times 10 to the minus 4 centimeters. All right, we see, actually I want to show you some other thermometers. So a thermometer is a great example of where linear expansion comes into play, but there are all sorts of different thermometers. Now these are the most common types. We use the mercury thermometers with the silver fluid inside of it, and then we also use alcohol thermometers. They usually appear red because, well, alcohol is clear. But there are some other types of food thermometers, and I have a little video. This is from, I think, Kansas State or something. It's like a food science department, and they put together this video about different thermometers. They're going to talk just about the thermocouple and the thermistor and how these are different. This is short. We'll start it. We'll likely get into these when we get to circuits at the end of the semester. Thermometers. And these two thermometers that she was talking about, the thermocouple and the thermistor, they every thermometer, you're really just trying to take something that changes with temperature and calibrate it so that it's known for certain temperatures. So for the thermocouple, they take 2 dissimilar metals, and when you heat them up to a certain temperature, they produce a voltage, an electrical current. We'll talk about that later when we get into circuits. The thermistor is very similar. It's a resistor, and when you change its temperature, it changes its resistance to current. All right, so if you have a higher temperature, you might have more current. And then you calibrate that to the known temperatures that you want to use. And then like with the mercury thermometer, you measure the length of the column of mercury depending upon which temperature it is. There's also another type of thermometer that you use, particularly in your kitchen. Most of you probably have this type of thermometer. It's just like a little round dial with a metal rod coming out the back of it. You'll see those. Now those operate by a different thing, by a different method, but they still use this linear expansion. And I think it's kind of interesting. This is similar to what you might have in your home for your thermostat in your house. Let me show you first. Let's say that I have 2 metals. I have a metal here, and then I have a metal that's connected to it right here. So I have 2 metals. And let's say that the alpha, the coefficient of linear expansion for this is, I don't know, 1 times 10 to the minus 6, 1 over degrees Celsius. And that the alpha for this one is 2 times 10 to the minus 6, 1 over degrees Celsius. What's going to happen when I heat up these two metal strips? They're connected to one another. They're welded to one another. What's going to happen when I heat up this strip? They're both going to increase in length, right? Are they going to increase in length by the same amount, given a temperature? No, which one is going to increase a greater amount, the blue or the red? The blue one's going to increase a greater amount because it has a larger coefficient of linear expansion, so then the blue will increase. And so what's going to happen to that? Is it going to move to the left or is it going to move to the right? So which direction? It's going to move to the right. So this is called a bimetallic strip when you have these two metals that are put together like this. And if I heat it up, if I drive the temperature up, so if delta T goes up, the blue side is going to heat up more quickly, or is going to expand more quickly than the red side, and you're going to get something that looks like this. You'll get the blue side here that will expand, and the red side will expand too, but just not as quickly. So it's going to cause the whole strip to bend. And so on that kitchen thermometer that you have, it looks like a dial. You have an arrow with some numbers here, and then it has this rod that comes out that you stick into the roast or whatever. What this has inside of it is a bimetallic strip that's wrapped up in a coil like this. So you have one metal that's wrapped up in a coil, and attached to it you have another metal. All right, so I have this bimetallic strip that's all wrapped up inside of there like a coil. And like I said, in some of your older thermostats in your home, you'll have these things as well. See, any of y'all have the old thermostats, not the digital kind, but with like the dial on it? Yeah, we do too. Actually, we just got rid of it. But on those, if you take the cover off of it, you'll see a little coil of metal inside of it. And that's this coil right here. So when your temperature increases or when it decreases, that coil will either cinch up or it will relax itself like a spring. And that's going to cause the needle, the coil is attached to this needle, going to cause it to change the reading of temperature, which has been calibrated to give you the correct temperature based on whether that coil is cinched up, if it's, what's the right word? You know what I mean, right? Like if it's bound up tightly or if it's relaxed. So lots of different ways to measure temperature. We see thermal expansion elsewhere. Like, for example, we see it in bridges and buildings. You know, a bridge can be pretty big, and likewise for a building. And so while concrete, just a small piece of cement or a small piece of brick might not change size very much just based on itself, but when you have a whole building that's made out of brick and you have constantly the cooling and the heating up from day to day that occurs, this linear expansion can be fairly significant. You might have seen, let me see if I can pull one up on the internet right quick. I didn't bring one with me. But as you're going across some of these big bridges that we have in the state, you might have seen these joints in the bridge. There we go. You ever seen a joint like this on a bridge? That's to account for the thermal expansion of the bridge. So during the day, when the bridge heats up and that cement or the asphalt or the steel that makes up the bridge, when it expands, this joint will move together closer. And then in the evening, when it contracts again, that joint will come apart. So it'd be kind of cool, I think, actually, to make a video of this, to watch it like a time-lapse video over several days. But I've never seen that. Okay, so that's a thermal expansion joint. And it's just required to account for the expansion of these very large objects. You have similar things in buildings as well to account for the expansion of the materials within the building. All right, so we see it in bridges and buildings. As I've already said, we see it in thermostats, like your old home thermostats. that coil of wire inside of it. You also see it like in the creaking of a heating stove. So when you turn on your oven and it's slowly heating up, sometimes you'll hear creaks, and that's just because the stove is slowly changing shape as it begins to increase in temperature. Now water, on the other hand, is quite a bit different from most materials. It's quite a bit different from almost every material. How is water, in this way, different from most materials? And it's a very important difference for the state of our planet. How is water different from other materials? Most materials, when they heat up, they expand, and in converse, when they cool off, what do? They shrink, right? They get smaller. What does water do when it cools off? It does what? It expands. So ice actually expands. When you freeze water, it gets bigger, right? Y'all ever put like a plastic bottle in the freezer, and then you pull it out later? What's happened to it? So, right, it's trying to bust out of the container. And if you put too much water, it'll pop off the top or put a crack in the container. And that's because water expands. Now, why is that important for the sake of our planet and for the sake of life in general? Because what does ice do when it's in water? It floats, all right? So when you have, because it expands, it's like a piece of styrofoam in a big lake. It floats right up to the top, and then it acts as an insulator for the water that's below it. If it sunk, you can imagine that the water on the top would freeze, and it would sink to the bottom, and then the water on the top would freeze, and it would sink to the bottom. The water on the top would freeze until the whole body of water would be frozen. And that would be very bad for us. Like our whole planet would be like a big chunk of ice. All right, so water is different from most materials just because when it freezes, it gets bigger. All right. We're going to look now at density, which is related to this. You probably know what density is. I'm just going to define it for you again here. Density is the mass per unit volume. The amount of mass per unit volume. And objects, they can have the same mass, for example, but they can have starkly different densities. So for example, iron has a much higher density than, say, feathers, right? You can still have, say, a ton of feathers and a ton of iron, but they're going to occupy a much smaller space because one has a higher density than the other. We're going to define density in this way. It's the mass per unit volume. It's going to be the Greek letter rho, and it's just mass over volume. The units for this, the SI units, are going to be kilograms per cubic meter. But often we see the units of density in another unit, and that's going to be grams per cubic centimeter, or grams per cc. And just as a point of reference, just to give you an idea of what these are, 1 kilogram per cubic meter is equal to 1,000 grams per cubic centimeter. We'll get into Archimedes' principle, but I've already stated this. Let me restate it. That when water freezes, the volume of the water increases. So what happens to the density? If my volume gets bigger, what happens to the density? It's going to get smaller, right? so the density will decrease, and this is what causes the ice to float. So ice floats. Y'all seen density before, right? High school physical science, likely, chemistry even. All right, let's do a quick example. Let's say I have a liter of blood, and I want to know what is the mass of a liter of blood. You have some homework questions like this. There's a table in your book. I don't have my book, but there's a table for densities of certain materials. I'll have that on the equation sheet. But the density of blood is very close to the density of water. Does anybody know what the density of water is, by the way? What is the density of water? It's equal to 1, right? So the density of water is 1 gram per cubic centimeter. And so the density of blood, which is made up of mostly water, is 1.05 grams per cubic centimeter. This is in a table in your book. As I said, I'll provide that on the equation sheet. So I want to know what is the mass of a liter of blood. Well, I know that density is equal to mass over volume. So I can cross multiply these, or I can multiply both sides rather by V. Cancels out, and I get an expression for the mass. The mass is equal to the density times the volume. That's going to be 1.05 grams per cubic centimeter. And now we need to convert this liter of blood into a unit of volume. Y'all know what a cc is? A cc is equivalent to a milliliter. But who can tell me what cc stands for? It's a what? It's a cubic centimeter, right. So 1 cc, that's just an abbreviation for a cubic centimeter. So 1 cubic centimeter is equal to 1 milliliter. And then I can do a conversion. I can find that, that a liter then is equal to 1,000 cubic centimeters. Let me do that off to the side here. I have 1 liter. I want to convert it into cubic meters. So I'm going to first convert it into milliliters. 1 liter is 1,000 milliliters. Then I'm going to convert it into centimeters. 1 milliliter is 1 cubic centimeter. And then in 1 cubic meter, there are 1,000 cubic centimeters. You won't have to do that conversion. I just want to show you here. So, well, that's not right. What did I do wrong there? It's 10 to the 6. I'm sorry. No, sorry. Here, this is not 1,000. It's 10 to the 6. It's a million. 1 cubic meter is 1,000,000 cubic centimeters. All right, so my 1 liter then is equal to 1,000 cubic centimeters. That doesn't work out right. I'm sorry. Don't worry about it. Just forget the last 30 seconds, okay? Because you don't have to do that anyway. All right, a liter is 1,000 cubic centimeters. So I'll need to include my volume here. So the mass of my blood is going to be 1.05 grams per cubic centimeter times 1,000 cubic centimeters. And then that gives me the mass of the blood, which is going to be 1,050 grams, about a kilogram. All right. Don't worry about this conversion between liters to cubic centimeters, but you do need to know that a cc is a milliliter and that a cubic centimeter is a cc. All right. Is that clear? All right. Yeah. Okay. We clear? All right. You want to see something, this website? This is not related to class. Y'all care? Yeah, that's the right answer. Uh, I'm doing this bike tour I told y'all about. There's this website that you can go to. Have I showed y'all this? It's called crazyguyonabike.com. Crazy guy on a bike. And it just has like journals of people that take off across the country and ride across the country on their bicycle. Or maybe not even across the country. Sometimes they're shorter rides, like they'll just go across the state or whatever. Or sometimes, like there was one I saw that goes from South America to the United States on a bicycle. Isn't that cool? And they're usually self-sustaining. Like they carry a tent, they carry all their food, and sometimes they'll stay at like a hotel or whatever. But usually they just camp out wherever. Like this is, they sort of highlight one every week or so. This lady, she was a biology major at Tempe, Arizona. I think that's ASU. And she just graduated, didn't have a job, so she said, well, her husband was in D.C. Well, I'm going to go home. So she hops on her bike and goes home to D.C. And then you can click on them, and they have photos of their trip. I think her husband rode with her the first bit. That was them, like at a restaurant. And they're just sort of like stories about what they encounter in their travels. That was kind of cool, huh? Yeah, y'all could do that. Like when you graduate, you could just take a few months off and ride across the country. All right, so you can consider yourself enriched. Let's look now at heat. We're going to define heat as energy that flows as a result of temperature differences. Energy that flows as a result of temperature differences. So, if I have a really hot thing here, a really hot block or whatever, and I put it up next to a cold thing here, the blue is cold, then I'm going to have a flow of energy from the hot thing to the cold thing. I'm going to call this energy Q, and we're going to call that heat. Anytime that you have energy flowing from a hot thing to a cold thing. And by the way, that's the correct way to talk about the flow of heat, flowing from hot to cold. So when you leave the door open and then somebody yells at you, what do they usually say when they yell at you? You're letting what? Yeah, you're letting the cold air out. In the summertime or in the wintertime, they say you're letting the cold air in. That's not really the correct way to say it. It's really, oh, you're letting the hot air out or you're letting the hot air in, because heat travels from hot to cold and not vice versa. All right, that's just sort of the correct way to talk about it. So heat always flows. In nature, heat always flows from hot to cold. And so when we talk about heat, we're sort of truncating this, but heat is going to be the same as basically as heat transfer. So whenever we're talking about heat, we're talking about the transfer of heat. We're just sort of truncating it. Instead of saying heat transfer, we'll say heat. We can determine if we have these two objects of dissimilar temperatures or of a change in temperature, we can determine the amount of heat. This Q is going to equal to the S times M times delta T. You might have seen this before. Instead of S, this is the specific heat. You might have seen it as a variable C. Have y'all seen this expression before? Q is equal to MC delta T. Y'all seen it at all? Okay, I'm just going to stick with what the book has because they use an S for this variable. And that's called the specific heat. M is the mass. You just erase this. You might see C elsewhere, but I'm going to get rid of it. And then delta T is the change in temperature. the specific heat is pretty important. The specific heat for a substance. What's that? Oh, Q is heat. Yeah. So Q is heat. Q is the heat transfer from a hot to a cold object. Or if I have, this is also saying if I raise the temperature of an object by a certain amount, then Q is the amount of energy that's flowed into that object. Or if I drop the temperature by a certain amount, then Q is the amount of energy that has left that object. All right, so this term specific heat, which we're listing with the variable S, is it says how much energy is required to raise the temperature of a substance. You know, different materials have different specific heats. And you probably in your head have a pretty good idea of comparing the specific heats. And we're just sort of fairly well equipped to comparing specific heats just in our mind. So let's say that I have a piece of metal. All right. How easily is it to raise the temperature of that piece of metal? Is it easy or difficult? Easy. What about a piece of wood? Is it easy or difficult to raise the temperature of a piece of wood? It's very difficult, right? So which has the higher specific heat, you think? The wood or the metal? The wood has a much higher specific heat than metal because it requires a lot more energy to raise the temperature of the wood than it does to raise the temperature of the heat of the metal. We see a lot of effects of this. Like if you go to the beach, you'll often feel winds that are traveling in either direction. Either the breezes will travel out towards the ocean or they'll travel in towards the beach. And that changes as we go throughout the day. Let's say that we're in the heat of day. We have our hot sun up here. And we have sand. And then we have water. All right? In the heat of day, which of these is hotter? That is, which one heats up quicker during the day? The sand is a lot hotter. All right? That's because sand has a big or small specific heat. It's a very small specific heat. So when the sun comes up, it starts to heat up that sand, and it heats it up really quickly. And that's why when you go to the beach on a sunny day, you want to wear your shoes out because the sand can get very hot. Right? So in the middle of the day, this has a low specific heat, so it heats up quickly. And the water, on the other hand, has a very high specific heat. Water is a very good insulator, so it's very difficult to raise its temperature. It has a high specific heat in comparison to sand. So it doesn't heat up as quickly. So I'm left with these masses of air above these. I have a hot mass of air here, the air above the sand. And what is that hot air going to do? It's going to go up, right? Hot air rises. So this hot air is going to go up as the hot air rises. And then the air that's out here across over the water, it's going to move in to replace that hot air that rises. So in the daytime, when the sand begins to heat up on the coast, that breeze will move in off the water. Now the reverse happens in the evening. If we consider the evening time, now instead of the sun being up, that's supposed to be a moon. We have sand. This is our sand now. And remember, it has a low specific heat. So not only does it heat up very quickly, it also loses its energy very quickly. So it cools quickly. And that water that has been sitting in the sun all day, it has a high specific heat, so it takes a long time to cool off. So the water then is still warm. All right. Objects with high specific heats don't change their temperatures very readily in either direction. All right, that's just like with wood, right? It doesn't either cool off nor heat up very quickly without a lot of transfer of energy. The same is true for water. So that water will heat up all day, slowly gaining energy as it heats up. And then in the evening, it'll maintain much of that energy throughout the night as it slowly dispels the heat into the air. So here, in the evening time on the beach, we get this hot air rising here. The hot air rises. And then the air that's above the beach will move in to replace it. So during the daytime, we have breezes that move in off the ocean towards the beach. And then in the evening time, for the same reason, but it's switched now, the air moves out towards the ocean. There's a really cool thing. Have you ever seen this show, Frozen Planet? It's a BBC documentary series that sort of goes through the North and the South Pole and all the changes that go on there. They have a different thing that occurs there where in the wintertime, or as the spring thaw is coming about, the sea ice will be melted, and then that water will warm up quickly because on land it's still covered in ice, and that ice takes a long time to cover up, to heat up. And it creates these particular winds. Let me just show you the video. I think they're called, I forget what they're called. Let me just show you. Katabatic winds, katabatic winds. So this is the same effect. Let's do an example. I want to know how much energy or how much heat is required to increase the temperature temperature of 200 grams of water by 5 degrees Celsius. And if you remember the specific heat of water, that is S, is equal to the number of calories required to raise 1 gram of water by 1 degree Celsius. How many calories are required to raise 1 gram of water, a temperature of 1 degree Celsius? It's the definition of a calorie, so how many calories to raise 1 gram of water by 1 degree Celsius? Y'all know this. How many? It's just a single calorie. So yeah, so 1 calorie is required to raise the temperature of 1 gram of water by 1 degree Celsius. So the specific heat of water then is just 1, and that's just based on the definition of a calorie. All right, so try this on your own. I'll give you a little head start. I just want to know how many calories to raise 200 grams of water by 5 degrees Celsius. We'll call that part A. And then I want you to do the same thing for 200 grams of lead. And the specific heat of lead, as I said, there's a table in your book. The specific heat of lead is 0.03. Notice it's a much smaller specific heat than water. So if I want to know Q, it's going to be SM delta T. That's 1 calorie per gram degree Celsius times my mass, which is 200 grams, times delta T, which is 5 degrees Celsius. That's my change in temperature. So that gives me 1,000 calories. So 1,000 calories to raise the temperature of 200 grams of water by 5 degrees Celsius. And then similarly down here with lead, is it going to require more or less energy to raise it by that amount? More or less? It's got quite a bit less because it has a lower specific heat, so it requires less energy to increase its temperature. So Q is SM delta T. That's going to be 0.03. That's in calories per gram degree Celsius times the mass, which is 200. That's 1,030 calories. So you see a lot less energy to raise the lead because it's a metal and it has a much lower specific heat than water than to raise the temperature of the water by quite a bit. I have a little audio clip I want to share with you. This is how we determine the caloric content of foods, is that we determine how much energy is in it to raise the temperature of a particular substance by a certain amount. And so this is just a clip. They're visiting a lab where they determine the caloric content of food. It's an audio clip, but it's still fairly interesting, I think. Can I come away from this for a moment? All right. That's pretty interesting, isn't it? So that's how they determine the food content. It's very quite simple. I mean, they just explode these little pieces of food and then measure how it affects the change in temperature of the water. So they're just converting the food energy into heat energy, and then those are equivalent. You can just say, well, this is so many calories. All right? I thought that was interesting. All right. Let's look also at phase changes. We're going to talk about evaporation and sweating and how it cools the body next time. But phase changes will come very important into this. So it requires energy to increase the temperature of a substance. It also requires energy to change phases between certain substances. All right, so we can change phases going from a solid to a liquid to a gas. When we go from a solid, we convert into a liquid. You remember those solids have very rigid bonds that hold the materials very closely, tightly bound to one another, so the atoms or the molecules don't move with respect to one another. So in order to convert a solid to a liquid, we have to put in a lot of energy into that transition to convert it from a solid to a liquid. And then similarly, to go from a liquid to a gas, we have to also convert our input a lot of energy as well, because those liquid bonds are still fairly close to one another, and you want to pull those molecules or atoms apart from one another in order to create a gas. These energies are called latent heats. And they describe the amount of energy required to convert a material from a solid to a liquid or from a liquid to a gas. Right? We're going to call HF. This is the latent heat of fusion. This is the energy going from solid to liquid. So converting, say, from ice to water. And HV is going to be our latent heat of vaporization. So the energy required to go from a liquid to a gas, or from a liquid to a vapor to a gas. I always think fusion, it reminds me of solids because I imagine those molecules, those liquid molecules being fused together into a solid. And then for the latent heat of vaporization, V stands for vapor, which is just another name for a gas. These aren't actually energies. These are energies per unit mass. So if I want to actually calculate the energy required to go from solid to liquid or liquid to gas, I'm just going to multiply it by the mass. So the energy to go from a solid to a liquid would be the mass times the latent heat of fusion. And then the energy required to go from a liquid to a gas will be M times the latent heat of vaporization. Right? So these are called the latent heats, going from solid to liquid and liquid to a gas. Let's do a quick example. Let's say that I have 800 grams of water at 0 degrees Celsius at a temperature of 0 degrees Celsius. So I have this water. It's at the freezing point of water, but it's not yet ice. Right? I have 800 grams of water at 0 degrees Celsius. And then I remove heat from the system at 15 calories per second. (15 calories per second). I want to know how long does it take for all the water to freeze. Just because I have water at 0 degrees Celsius doesn't mean that that I have ice, because I have to take out this extra heat of fusion in order to make that water become ice, to remove that energy and to make it become ice. All right, so I can determine my amount of energy. Q is just the mass times the heat of fusion. So I have 800 grams of water. The heat of fusion for water is 80 calories per gram. So the heat of fusion for water is 80 calories per gram. For 1 gram of water, I need 80 calories to make that transition from ice to water, or vice versa. So it's 800 grams times 80 calories per gram. So that's 64000, 64,000 calories in order to go, that amount of energy you have to take out in order to convert that water into ice. And then if I want to know how long it'll take, I have a rate up here. I'm taking out 15 calories per second. So I would say that 64,000 calories is going to equal 15 calories per second times that time. Right? And so I can find my time, just dividing both sides by 15. And that's going to equal 4,270 seconds, which is approximately about 1 hour and 11 minutes. If I'm taking out energy at this rate, at 15 calories per second. You'll see some homework questions like this. These are good practice questions for the test. You're very likely to see things that are similar to this. I know there's a lot of sort of problems in this, but largely it's just being able to plug in numbers to the equations. So just make sure that, I'll try to get your equation sheet to you soon. Just make sure that you practice this and you're able to use those effectively. I'm going to return your quizzes right now, and then we'll come back to this on Thursday. I'll have a few minutes at the end. If you have some questions about them, I can answer your questions. Also, don't forget that the solutions are online, but I'm always available to go over any questions that you might have.